it can be quite tricky to actually measure current consumption, because if you have a board with microcontroller, then the current consumption is going to keep changing constantly. So what is the trick? How you actually, do it?
Yeah, exactly. That's the problem, especially if you have a microcontroller. But these devices, they have an RF interface, so you may have some transmission and receiving over an RF interface. So the current consumption will vary over time. So basically, what you need to do, the instruments that you need to do, is a power profiler, or sometimes it's called a DC energy analyzer. So basically, what this device does is basically measuring the current, like sampling the current at very high frequency. We are talking something between 10 kilohertz to 100 kilohertz, and then recording all the measured current value and streaming them over, for example, to a PC, where they will be logged, they will be showed on the graph, and you can measure the integral of the current, which is basically how many coulombs we are taking from the battery. And with this number, you can come up with how long the battery is gonna last. So
So what can we
that's
use? I see here are some examples.
exactly. So there are different devices like this on the market. In this example, we're gonna use the Joule scope from JetPerch, specifically the JS 110. There is also a newer version, but unfortunately I don't have it yet. So we're gonna use the old device. There are other devices on the market, like Nordic has their own power profiler kit, but personally I prefer the Joule scope, and we're gonna use it for these experiments today.
I would like to add. Actually, I heard about this Joule scope from number of people, so I believe it's quite popular for this kind of measurements. This is what I wanted to add.
It is, and it's popular, it's flexible, there is a community. So Matt Libert is the designer of these products, and there is a community on the web. So if you have questions, you can ask them. And it's flexible in terms of hardware, in the sense that you can change the front panel, which is basically the means that you use to connect to your hardware. And we will see that we have designed a custom front panel to connect to our boards. And also you can also it's flexible on the software side on the PC, so you can run scripts, and so you can integrate a Joule scope, for example, in your testing machine. So you can do all this kind of stuff.
Can we have a look on website? I'm just curious, how much does it cost?
I don't remember how much I paid. Let's see for the newer version. I don't know if there is a price on the web. Yeah, it's 1,000 for one. Yeah. So yeah, but
okay,
it's,
so
it's,
it's not
definitely
cheap, but
it's definitely worth. I mean, if you really want to measure power consumption precisely and size the battery properly, you really need that device.
Because this can measure also like very, very low current. It can switch very quickly between high current and low current, or
So let me explain what's the peculiarity of these devices.
Okay.
So basically, what you have here you go. So you got your battery, and then here you got your duality. And basically the DC energy meter or power profiler is basically like an amp meter that you place between the battery and the DUT. But what's the particularity? First thing, it has a very high dynamic range, because the DUT can draw 1 amp, so we are in the amp region. For example, if you have a cellular modem which is transmitting, you can easily go up to 1 and 2 amps. But then when you go back to sleep, you can go down to, I don't know, few, like 1 microamps, so very low current. So this device has to be first thing very precisely in both current ranges. So the current profiler has a high dynamic range, so it can be very precisely along all this range. And the other thing has to switch between current ranges very fast. And the DC meter basically solved this problem. The DC energy analyzer solves this problem.
I can see because these are like big changes, like from what is like 60 milliamps up to 460 milliamps in very short. I don't know what is the time on this.
Yeah, no, here is seconds. We'll see that in details. But basically, we are moving from 5 microamps, where we are in sleep, to have something around 500 milliamps. And it happens in a few milliseconds. So yeah, we will see that in more details. But
Okay,
yeah,
so what kind of
that's the
setup do
range
we
we're
have?
operating. Right. So basically, what we have done, we have developed a custom board to characterize the ESP32. And this custom board can be plugged to a custom gyroscope front panel. So basically, at the end, you have this kind of setup, which you can probably also see in the webcam. So we got the ESP32, which is powered by an USB cable. Actually, it's powered through an LDO, but basically we have a USB cable, which is the source, the power supply source. So the 5 volts goes into an LDO, which regulates 3.3 volts, which is the voltage that you need to power the ESP32. And this 3.3 volts will go into the gyroscope, which will acquire the current and then flow back to the ESP32 and then close to
Why
the
did you
ground,
choose ESP32 for this board? Because the same way we can measure basically any board or any microcontroller or anything what we need.
Yeah, so basically we choose the ESP32 because we will need that for some projects with the company Altotech, which I'm working with. And we decide that we want to characterize this device because we use extensively in our projects. So we decide to do a custom board specifically for the ESP32. And with this, custom board, I also have like an IMU, so I can use the ESP32 to do something useful. I have the USB, so I can program and debug and talk with the ESP32 through USB. I have some buttons. I have like a cradle for an Arduino shield. So I can also use this board to play around with the ESP32 while measuring the power consumption. And if you're interested, with Altotech, we also have developed the same thing for the NRF52, which is another microcontroller that we use extensively with Bluetooth Low Energy. And in the future, if we were going to use another device like this, we can develop this custom board and reuse the custom front panel, which we have designed, which is unique, and you can share it with these boards.
Okay, so basically, how would you use this? I understand you would use it to measure current consumption for all the kind of different situations and stages for ESP32. So you can kind of very accurately calculate and predict for your specific application how much current is going to drive this your board with your application running on ESP32, and then you can calculate or estimate how long the battery will last. Correct? That's what we are going to do right now.
Exactly. So you want to jump directly on the measurement, or you want to go through the characterization and?
So is there something else what we need to explain before we jump directly to measurements? What is on the second slide?
Right. So I have a typical connected sensor application from hardware firmware, and then I don't know if you remember.
You can explain this. You can explain this.
Yeah. Okay. All right. So here, basically, I have just depicted a typical connected sensor application from a hardware point of view, a firmware point of view. So this is a very simple, just to make an example how we're going to measure power consumption. So from a hardware point of view, our DUET is basically made by a battery, which is in this case is a rechargeable lithium-ion battery, but can be also a primary battery, which is the source of the energy of the device. Then there is a power stage, which basically takes the battery voltages and converts to a 3.3 volts for our circuitry. And we're going to make the calculation for two scenarios. The first one is using a buck boost, and the other scenario is using an LDO. So there are pros and cons to using those two solutions. So we're going to discuss that.
So we will compare which one is better and which one will long last.
Exactly. And then we have the ESP32, And also we have a sensor. But in this case, on the board, we have an SDST, an accelerometer, and gyroscope. So it's a 6-axis MEMS, basically. And from the firmware point of view, what we're going to do is something very simple. From time to time, we're going to wake up, acquire the data from the sensor, connect to the internet, and then sending the data to the cloud, and then go back to sleep.
This
And
can be quite
repeat.
difficult to estimate if you don't use special device to measure the current. I don't think you can very easily actually come up with real numbers how long the battery is going to last.
Exactly. I mean, I can tell you how I did in the past before I
okay,
this
tell
device.
Me.
If
I'm
you're
curious.
interested. Yeah. So basically, what you did in the past is basically just based on the number on the data sheet and few measurement, but just measurement to measure the time of the events. So basically, so let's assume that this is your current. Basically, I was saying, okay, the device stays in sleep for this time of time, for this amount of time. Then it wakes up, and then it transmits. Then maybe it receives.
Okay, and then you, based on data sheet, you filled up the numbers, the maximum current consumption.
Exactly. I mean, if you look at the ESP32 datasheet, they give you some numbers on current consumption. They give you, I mean, the current is sleep. They give you the current when the CPU is running, but the modem is off. And they also give you the peak current on TX and RX when the radio is working. But as you can see, they varies depending on the speed of the network. And these are peak current, and not, here instead is the average current. So you end up with that, with the estimation is not precise. And basically what you end up doing is oversizing the battery. Just to be sure that you're going to last, the time that you want to last. But, IoT devices, sometimes they are small and the battery can be oversized. So this is, you can achieve like the edge of technology using this kind of
I have another question.
Way to do the measurement.
So how did you know, or how did you recognize these different stages? Did you use did you toggle a pin or something?
Yes, exactly like that. I mean, with the microcontroller, you can toggle GPIOs, and then you can, with an oscilloscope, logic analyzer, you can measure the
how long
duration
it is
of
in
the
specific state.
Exactly.
Okay.
Exactly.
So this is maybe a good tip for everyone who doesn't have this kind of expensive measurement tool. This is cheaper way how to calculate or estimate how much current your specific board running specific application can drive. Okay, we can go back to our presentation.
Okay, so I mean, during our development stage is before just jumping directly to measuring the current consumption here in with the final application, we also use the Joule scope to characterize the hardware and understand if the board is consuming the right amount of current in the different power levels. So because if you have your application running, it may be tricky to understand, okay, now is it sleep, now is transmitting, now is it in idle. Instead, what we usually do is develop a custom test software, which we call the console, just because they expose the console on the UART, in the USB in this case. And then we can ask the microcontroller to go in the different power consumption stage, and we're going to use the Joule scope again to measure the current consumption. So it can be used to validate your hardware and that the board is performing as expected.
So through UART, you can actually change the mode which is running on the ESP, like now transmit something and you will see, and then you can measure it. Now go to sleep. You can measure the sleep.
Exactly. I can show you how to do it if you want. So, together with the board, we also provide an Arduino board package that you can download through the Arduino board manager. So, I mean, if you don't know how to do it, there is guides on the Arduino website. Basically, you add the URL of our GitHub on the Arduino board manager. And then with the Arduino board manager, if you look for R2Tech, you can find the board package. So you can install it. And once you have installed it, there are some examples, and we're going to use the console example, which are already flashed on the device. So once you have the console exception up and running, you basically have a console here, and you can talk with the device.
So basically, this is the test application, and anyone can download this, and they can change the, they can control the mode when their ESP, or in what their ESP32 board is running.
For example, I'm sending these commands. Usually the LED's turning on the board.
Yeah.
You can probably see on the card. Okay.
Switch it off,
so,
because I didn't see it switch it on. I was not looking at the camera.
So now it's off.
Okay, off. Okay, I see it.
On again.
Okay.
And off again.
Okay, what are the other commands?
Okay, so let's. Okay, so we're gonna do one thing. So we're gonna keep this here, and also we're gonna turn on the gyroscope live stream.
Oh, I see that.
So that's the gyroscope. That's the gyroscope interface. So here we have the current in like the waveform mode. So it's like looking at an oscilloscope, but looking at the current, and so you can see the current over time. And here is like watching at a multimeter. So we have like the current average every 500 milliseconds. We also have the voltage, which in our case is 3 volts, because remember, the gyroscope is between the LDO and the ESP32. So we are measuring the current that the ESP32 is drawing.
Yeah, okay.
So
yes.
I'm turning on the LEDs. But yeah, you can also watch the current here. As you can see, it's 39 milliamps.
So do you drive the LED directly with the current flowing through the pin, or there is transistor or something?
Yeah, there is an external transistor, but the LED is connected to the 3.3 volts, so the current is coming from the LDO.
Okay.
So you can see here.
Okay.
Remember, here we are measuring the current. Actually, the current which is going
from the LDO directly,
the LDO.
So which is powering the whole board. Okay.
Exactly. So it's powering the ESP32, the
and
LEDs,
and the sensor
and the IMU as well.
So we measure currents for all these devices. Okay.
Exactly. So oops, wrong command. It's off. Okay, and we are back to 27 milliamps. So the first thing I wanna show you is the effect of the CPU clock frequency on power consumption.
I'm very curious.
By default, the ESP32 C3 is running at 160 megahertz, which is quite reasonably high clock frequency. And if your application doesn't have to do too much calculation, like in our case, we just wake up, sample the data from the sensor, and send over to the cloud. We are not running any DSP or AI, edge AI computing. So maybe we are good enough at 80 megahertz. So let's see if we set up the CPU at 80 megahertz. You can see that the
19 milliamps. What was before?
Yes.
27?
26, 27. So yeah, almost a third less. So, if you can really live up with 80 megahertz CPU clock frequency, you can improve the current consumption just doing that with one single line of code.
By 30%, this will.
Exactly.
Yeah.
Exactly. And, this measurement, as I said before, that you can use this instrument also to validate the hardware. You can check if these measurements are matching the datasheet.
Okay.
You can see here with 160 megahertz, your current consumption with all peripherals on should be 28 milliamps. We got 27, so we are close. And 80 megahertz is 22. We are 19, so we are close. There is a variation, depends on how many peripherals are turned on and off. We are always in the middle, so because we have the USB on, but we have other peripherals off. But at least we know that we are in the right spot, and everything is working as expected.
Nice.
And we also, there is also deep sleep mode, which is the mode that we enter when we go in sleep. And let's see. So we're gonna enter deep sleep for 30 seconds.
Okay. 5
And that's
microamps.
exactly. So yeah, it's it's a very tiny current consumption.
So this
So we
is
want to
why
stay
if someone is designing IoT, they really should understand how to use sleep mode because they can save a lot of energy.
exactly. We want to stay in this mode as long as possible.
It's big
And
difference, very big
yeah,
difference.
yeah, it is. It is. And again, we go back on the data sheet, deep sleep with the RTC timer on, 5
5 microamps.
microamps. So we are, this is very good measurement because you can, with the low power devices, they are always tricky from a hardware point of view with leakage currents. It's very easy to have like, few microamps, maybe 10 of microamps of leakage current somewhere. You will have like a floating node or a pull down resistor somewhere. And you can easily lose, tens
Oh,
microamp,
you would see,
10 of
yeah, you would
microamps.
see pull down, pull
You
up
will,
resistor here. Definitely, it would not be
yeah,
5 microamps.
exactly. You'll see that, and then you can fix it.
But I'm very
So yeah,
surprised. Even the USB cable is connected, and you are using the UART console. Uh, it still can go down to 5 microamps.
yeah, because basically the USB data lines are basically connected to two pins of the ESP32. But when it goes in deep sleep, it basically puts these pins in a high impedance, so that there is no current draw on that pins, and they are like disconnected from the microcontroller.
Cool.
So that's how they can achieve this low power consumption. Okay, so let's try to do something more interesting, like connecting to the Wi-Fi. So
Transmitting some data.
yeah, so I'm gonna use this command to connect them to my local Wi-Fi network. So
Okay.
now everybody knows my password, but it's just local Wi-Fi network, so I don't care. And let's see. So here we can see that the current waveform has changed from before.
460.
Yeah.
Wow.
So we have a slightly higher average current consumption, but we can see that the waveform itself has changed a lot. So we can pause the waveform and go into it. So we can see that it should be every 100 milliseconds roughly. The radio is communicating with the Wi-Fi router. That's what is called the beaconing. So basically, it's just keeping the communication with the Wi-Fi router.
Oh, I didn't know this.
And
So basically, once you are connected to Wi-Fi, your current consumption is going to increase even if you don't transfer any data.
exactly. And you can see here that the current is going from 30 milliamps, 26 milliamps to 100 milliamps.
Yeah, and initially it was
And
much higher. Initially it was 460.
yeah.
So why
Yeah, no,
initially it was so high and now it is so low?
so I'll show you. It's higher when you start actually sending data over to the internet. I think here from time to time is connecting to internet, and that's why you have these higher spikes. I can show you how the current consumption where we actually sending data over to the cloud.
Okay.
So if we go back to our presentation, just briefly, a few words on MQTT, because we're going to use MQTT to send data over to the cloud. MQTT is basically a protocol based on TCP/IP. So once we are connected to the Wi-Fi, we can use MQTT to send data and receive data to the cloud using an MQTT broker.
So
And in this case,
MQTT is some kind of protocol or something which can give you option communicate your board with a system which is somewhere in the cloud and exchange some data like temperature.
Exactly. So you can imagine there is a broker in the internet. We're going to use a AMQX broker where we connect to this broker and we're going to send the data. It's called publishing in the MQTT world. And you can have a client on your PC, for example, this application MQTT.fx, which connects to the same broker, subscribe to that topic, and will receive the message that we send over to the internet. So we can use this client to verify that we are actually sending data over to the internet. I can show you. It's easier if I show you.
Okay.
So I will just check if we are still connected to the Wi-Fi. Okay, we are connected, and that's our local IP address. So I'm gonna connect with the device to the MQTT broker, and I'm gonna send a message.
Broker is
saying,
basically some kind of website or service running in cloud, yeah, or somewhere on internet.
Exactly. And you can see I'm publishing a message, hello, Robert. And we can see with the client, which is connected to the same broker and subscribed to the same topic, that we are receiving the message. So we are actually sending data over to the internet.
Okay, over Wi-Fi. So let's have a look.
Yeah.
I'm curious.
And let's have a look. Yeah, that's when it happened. So yeah, you can see here that we got huge current spikes up to 460 milliamps actually. So, even though, and the waveform is also different in regards to the beaconing that we have before. So the average current consumption is higher here, but also we have these spikes of current.
I would like to point out this because some people, if some people experience, if the board is not designed properly, some people may experience some kind of random behavior, and often it can be if they use this kind of modems or Wi-Fi's or something, and they don't calculate the power consumption properly, they don't include support for these high current peaks, and then once these peaks are not delivered, or they can introduce a lot of noise into power supplies or power rails, and then whole system will behave very randomly. So
Exactly.
when designing boards, they have to design it properly.
Exactly. I mean, the way, for example, I do it is, so on the datasheet, actually they're saying that you need the power supply able to deliver up to half of amps, so 500 milliamps. So the way I do it, for example, when I design my board, I put the ESP32 in deep sleep, so I know that it's not drawing current. And then I'm using an external load to make sure that I can draw up to 500 milliamps from the power supply, and the power supply is still alive. So then I'm sure that when the ESP32 is working, I have no problem with that. So you need to design the power supply to deliver not the average current, but the peak current.
Yeah, because by normal measurement, you would never see these 460 milliamps peaks.
Exactly. And so, yeah, I mean, just for completion, I can show you that we can also receive data from the internet.
Okay.
So let's see if I subscribe to a topic. I'll fail. Maybe I got kicked out from the server. I need to connect again. Okay. So if I subscribe to the topic with my IoT device, then basically if on this server and publish something, so from this client I'm sending over to the cloud, and then the cloud is sending the message back to the device. So it's basically showing that we can do the communication in both directions.
Okay, so basically this is also a very nice example if someone is building something where multiple devices need to be connected together and they have to talk together, like number of sensors, talking to a microcontroller or processor board. They can use this kind of system and MQTT, and these sensors, they can send all this information to the microcontroller board, and that board can show it on display or something.
Exactly. I mean, you have two boards like these, which they can communicate over MQTT through the broker.
Yes.
So you think just the broker is someone holding the messages. So, a device can send a message to a broker, and then the other device can subscribe to the same message and then receive the message from the broker. Yes.
And it doesn't have to be only one device subscribed to one topic. There can be multiple.
Exactly. Can be multiple devices. Yes. And also you can have another web server which is subscribing to that topic and using the data for doing, showing on the dashboard or something like that. So you can put all these different, devices and web server together using MQTT. So it's very handy.
So how exactly is the server called, or the service what you are using for this?
Okay, so for this I'm using, let's see if I have
I'm just curious.
Yes, sure.
Because there are a number of different services.
So I'm using this, the broker is a public broker, which is MQX. And then I'm using this, this is the client installed on my PC, MQTT-FX. So you basically connect to this broker, and then you can use it and, send the data, publishing data, subscribing data. And
how much does it cost?
No, it's free.
It's free.
Yeah. This is I mean, it's free. I mean, as I say, everyone can see your data, because everyone who is subscribed to this topic can see your data. So it's a public broker, but you can use it for testing. I mean, when the device is going to deploy it in a real environment, the device, I mean, they're going to use probably a private MQTT brokers and private servers to hold all the messages. But yeah, so and then you can create accounts on the broker, so you can to log in you need a password and the user password, so it's a bit more protected. This is a public broker that you can use it for testing.
Okay,
and
so what else we can measure on our board, and then how do we actually calculate how long the battery will last?
Exactly. I think we done for
examples of different modes.
With examples. Exactly. So we know that the board is working as we expected. So we can jump directly to a real life application. So for doing that, I'm gonna use another program, which you can still find in the example. And basically, we're gonna wake up, we're gonna repeat the same thing every 10 seconds in this example, but we can tweak that and choose a different repetition time. Basically, what we're gonna do is, as I said before, wake up, sample the IMU, acquire the data from the IMU, connect to the Wi-Fi, connect to MQTT, send the data, and then go back to sleep.
So this is like real life application, which will read the data and send it out.
Exactly.
Okay.
So let's program the board with this this program. So it's taking it takes some time to program the board.
I'm curious how you are going to calculate the consumption.
Here we go. So let's start the gyroscope again. Okay, so here we go. We can see that we are around 5 microamps. Then we are waking up, doing something, which is sampling the data, sending over to the cloud, and go back to sleep.
And every 10 seconds. Okay.
Yes, and just to
verify,
seeing that we are actually doing something, we can see here the value that we are receiving from the accelerometer. Exactly. If I tilt my board, you should see the value changing. You can see that the value are changing. If I put it back flat, yeah, the values are changing. So here we go. So every 10 seconds, we are basically waking up, sampling the data, connecting to the cloud, sending the data, and then go back to sleep. So, okay, now that we are here, how I'm going to measure the current consumption. So there are two ways, basically. You can focus on an interval, measure the coulombs that you're taking from the battery and do the calculation. But we can talk about that. But there is a faster way. So, and a more precise way, because if you do that, you're basically relying on the fact that every time these intervals are using the same amount of coulombs. But that's not always the case. Sometimes these intervals can be a bit longer or a bit shorter, depending, how long it takes to connect to the Wi-Fi, how long it takes to connect to the broker. For example, here you can see.
Yes, I can see it's longer.
Yeah. So the way I actually do it, so when I have the device running here, instead of measuring the current, here on the multimeter, you can see the current consumption averaged every 500 milliseconds. Instead of averaging every 500 milliseconds, I use the accrue feature, which basically is averaging the current over time. So now it's every 5-6 seconds. That's the average current consumption. And the way I do it is basically I leave it run until this value is stabilized, which usually happens, after many intervals, repetition intervals. Let's say something between 20 and 100 repetition intervals. So in this case, if, for example, if I'm repeating this event every 10 seconds, I'm leaving it for, 1,000 seconds. So it's 100 repetitions. And then I take the average current. And that's basically the average current of your DYT.
Okay, and then you use this average current in further calculations.
Exactly. So basically, I have a spreadsheet that I use to calculate the lifetime of the device. And there are two different calculations based if you're using an LDO and a buck boost, but just start with an LDO for simplicity. So basically, I insert here the average current consumption, which let's see if it's okay. It's not
It's still
yet
changing,
converging. It's still changing, but I've already done this experiment for you, and for a 10-second sampling period at 80 megahertz is around 5.3 milliamps. And so to this current, you need to also add the quiescent current of the LDO, and to have the quiescent current, you can either measure the quiescent current of the LDO or get it from the data sheet.
So basically, I think that's the current which goes to the ground inside of the LDO.
Exactly.
It's kind of
Sometimes they call
power
it
consumption of the LDO.
Yeah, they call it the ground current or quiescent current.
Yeah.
So that's a section of the data sheet where basically they are showing the quiescent current in function of the load. So with no load is 20 microamps. With the full load, which is 0.5 amps, is 80 microamps. Since our average current is 5.3 milliamps, so we are very close to the no load condition, I pick it up 25 microamps.
Okay.
And then also you have the self discharge current of the battery, because the battery is not ideal. You may try to find this number from the data sheet. For example, for this battery, I found it a maximum value of 6 microamps and a minimum of 1 microamps. So I choose the typical to be around 3 microamps. You can be even more precise, because this current is usually coming from the internal protection circuitry. So, they give you the data sheet, the part number of the device they're using. If you go if you Google it, you can find it, and they tell you that typically is 3 microamps. So you can also take this in account. And so you sum all these three currents, and that's the average current consumption, basically, of your DYT. Now that you have that, and you have your battery capacity, you can estimate the lifetime. There is one last consideration to be taken in account for the case of the LDO, which is the fact that you can't really use the entire battery capacity. If you want, I can explain you it.
Yeah, okay, I'm curious.
Okay, so the capacity of this battery is 1300 milliamp hour, but just under the assumption that if you use the battery down to 3 volts. Instead, since we have an LDO, which is basically regulating, I can probably draw something here. So
yeah, there will be some loss on the LDO.
Yes. So we got the LDO, which is making 3.3 volts. Okay. But the LDO usually needs what is called a dropout voltage to work properly. In this case, is around 200 millivolts. So to deliver the 0.5 amps that we need. So it means that basically the device will work fine until you have 3.5 volts here. When the battery goes lower than 3.5 volts, you're not guaranteed to be able to regulate the 3.3 volts properly. So basically what you have to do is go into the discharge voltage curve and see, okay, if I can use the battery only down to 3.5 volts, how much capacity I can use in real life. And you can see that basically
90%.
You can use 90%. So you're losing 10% of your capacity. So in your calculation spreadsheet, you want to take that in account. So that's the usable battery capacity. And with that number, that's the number you're using to measure the battery lifetime, which in our case is around basically 9.2 days.
For the first example.
Yes, if we send data every 10 seconds. If we send data, less frequently, let's say every 30 seconds, then we can achieve around 30 days.
3 times more.
Yeah. If we send data every 300 seconds, we can achieve 240 days of lifetime. So you can see that, of course, the less frequent you wake up and send the data, you can save battery life.
Yeah, but it's like huge difference. 10 days and 240 days. There's like huge difference.
Yeah, it is. And there is also a difference. You can see I've done the measurement are also running at 160 megahertz, which you actually don't need it. I mean, the device behavior is exactly the same. You won't see any difference. But you can see, in the 300 seconds example, you lose 50 days. Yeah, or 40 days. Yeah, 40 days if you run 160 megahertz. And that's one single line of code.
Nice.
So,
and you have the, so this was for the LDO. You have example also for the buck boost.
Yeah. Okay, so let's do the calculation for the buck boost. So the average current consumption for the ESP32 is still the same because the buck boost is still regulating 3.3 volts. The difference is that with a buck boost, basically, going back on the drawing board, basically you got your battery, and then we have the buck boost, which regulates 3.3 volts. But the buck boost, since it's a switching regulator, can regulate 3.3 volts with a wider input voltage range. So can regulate 3.3 volts when the battery is 4.2 volts, like the LDO, but also when the battery is 3 volts, it can regulate 3.3 volts.
So we can use the extra battery, the 10%.
Exactly. So we can use the entire battery capacity.
And also, I think it's more effective comparing to LDO.
Yeah, it's also since we are, I mean, since I would say in the vast majority of the lifetime of the battery, we are dropping down the voltage from, let's say, 3.7, which is the average battery voltage, to 3.3. Yeah, the current we are drawing from the battery is actually lower than 5.3 milliamps. So we are drawing, something less because we are using a DC-DC, which is 90% efficient. And plus, you need to sum again the self-discharge current. So that's actually the current consumption that we take from the battery. And we can say that we can last 10 days in case of
first example.
The first example, exactly. But if you go to 300
days.
seconds, we go to 300 days, so extra 60 days. Yes. So if we compare the two, we can see that if you're fine, sending data every 5 minutes, basically. With the buck boost, you can last extra
almost
60 days. Yeah, almost a year. You can achieve almost a year with the buck boost.
But if you set up everything wrong, it will be 2 days.
Yeah. If you don't measure your circuitry and make sure that everything is working fine,
if there is no sleep, deep sleep.
Exactly. You need to use deep sleep, and of course the drawback of the buck boost is that it will cost more. You will add the complexity. You have an inductor, so you have to buy the IC, the inductor. You may have EMI problems, so you need to design it properly. But you can achieve better lifetime at the end of the day.
So this is a very good example to show current consumption of ESP32 in different situations. So I think everyone who is trying to design something with this currently very popular solution, they can use this, and I hope it will help them. And I hope many people will actually maybe consider to buy this this kind of very precise current measurement tool. I would buy it if if I really need it for application. I think it's definitely worth it.
Yeah, I mean, battery are expensive. So, if you can end up, using a smaller battery for your device, you're probably going to save money, in the long run when you, produce, thousands or hundred thousands of your devices.
Yeah,
So it's definitely worth it.
and definitely
There
even
is a,
uh,
yeah,
for software development, because I remember when I was writing code, and okay, I think my board is now in deep sleep. Is it is really in deep sleep? For how long? And so having this kind of scope, you can immediately see when you are writing software, you can immediately see if you are doing it right.
Absolutely. I mean, in Altutech, every firmware developer has a joule scope, and every time we develop a firmware routine, we measure what's the impact on the power consumption. So, this is a hardware tool, but it's mainly used by firmware developers because, maybe the hardware designer use it to validate the hardware, but then it goes in the hands of the firmware developers, and they have to use it to understand the effect of the firmware on the power consumption. Actually, I have an example later which I can show you. How you can tweak the firmware, and you can see that you can save
Okay,
power
let's have a
consumption
look.
just
Let's
tweaking
have
the
a look.
firmware. You want to jump to it, or
Yeah,
before
yeah.
I had another? Okay,
Or is
then
there
I'll.
something else what we would like?
Yeah, I mean, I want to show you another feature of the joule scope,
Okay.
because the joule scope is not only. I mean, you can mainly you can use to measure current, but it has also some digital inputs and outputs. So you can basically connect it to some GPIOs from the microcontroller. And remember before we were talking about toggling GPIOs to understand the different
Mode.
what
Yeah.
different mode. Yeah, we can do exactly the same here. I mean, if we look at this one of these events, we can see here basically.
Okay,
So
so zero is
if
like
you look,
input
yeah,
zero, or it's like
yeah,
kind of input into the joule scope and from your one of the pins on
exactly.
ESP32. Okay.
Exactly. I mean, if you look at the setup, there are two wires coming from the
Mm-hmm.
board, and are going to the gyroscope.
Mm-hmm.
They are ground, and one is a digital pin,
Mm-hmm.
which basically I'm just toggling with my software from time to time,
Mm-hmm.
and I can correlate the toggling of this pin with the current waveform.
Mm-hmm.
I have it here on the slide.
Okay.
So basically, when I wake up, I toggle the GPIO. Then I toggle it again when I done with the IMU sampling.
Mm-hmm.
Then I toggle it again when I'm done with the Wi-Fi connection,
Mm-hmm.
and then I'm toggling again when I'm done with the task.
Mm-hmm.
So I can understand the different current waveforms in the different stage of my routine.
Super useful.
So I can understand where I have to work to improve the current consumption.
Wow.
For example, here I can see that I'm spending a lot of time and coulombs actually when I'm doing the MQTT transmission, which leads to the example that I want to show you, and show you how we can tweak the firmware to save current consumption.
Okay. Let's have a look.
Okay, so I mean it's a very trivial example, but it can be just a ground of food for thought for different types of application, which you have probably a similar condition. So basically, what we want to do with this program is do exactly what we did before, but instead of sampling the sensor just once, we want to sample it 10 times, let's say. So we wake up, we sample the sensor 10 times, and then we want to send these 10 data over to the cloud. Okay, so let's program the board with this new program.
And I guess we'll find out it consumes a lot and we could do it better.
Exactly.
Can you use, I think you already mentioned, you can also use like coulombs to calculate the how much the battery will last. So how would you do it?
Yeah, I mean, we can do exactly for this example.
Okay.
So we can see we are waking up and then we are sending the data to the cloud.
10 times.
And yeah, we can see here that we received 10 different datas. Okay. So basically we can see here that, looking at the GPIO, we are waking up, sampling the data, connecting to the Wi-Fi, and then doing 10 different publishing on the server and sending the data 10 times. So if we want to measure the current consumption of the Coulomb consumption of this event, which is basically, between deep sleep modes. So here we can see that we are basically drawing 100, let's call it 130 millicoulomb from the battery. So if we want to use that for calculation, basically, you can do it with the spreadsheet. It's very simple. You say during these events, I'm drawing like 130 millicoulomb, right? Plus, I have also a bias current. So it's basically your current in deep sleep, which is the 5 milliamps from the ESP32 plus the 25 microamps from the LDO plus the battery, which leads to basically a bias over the 10 seconds, because we are repeating this interval every 10 seconds. So that's basically how many millicoulombs we take from the battery every 10 seconds due to the wake up event and due to the current bias, so the Biaxian current. You sum it. So basically every 10 seconds you take from the battery 130.33 millicoulomb. So your battery is 1170 milliamp per hour, because that's the example of the LDO. So you're not using the entire 1300 milliamp hour, which basically is you multiply by 3600, and that's how many millicoulombs we have inside the battery. So if you divide this number by this, you know how many times you can repeat this 10 seconds interval. And then if you calculate it and you translate it back again in days, it will tell you how long you're going to last. So you're going to last 3.7 days in this case. Okay.
So it's much less actually than if you are sending only one value.
Yeah, it is. And I mean, so you can use this method, but as I said, this is not precise, because basically you're just taking one shot of the waveform. Depending on on the how long it will take to connect to the broker, these shapes can be different from different intervals. So you're not really doing the like a typical measurement. You may be taking a good interval or a bad one. So it's better to use the actual and do the average over time.
Okay.
And remember, we are running this at in typical condition at root temperature. If you want to do a very precise measurement, you can also do it changing the temperature and changing other
-40
factors. Exactly. Yeah, you need to find a way to connect to the temperature chamber, but yeah, you can do it. So let's go to the software and do a simple tweak. Because what we are doing at the moment, let's think, we are sampling the sensor 10 times and then sending these 10 different data over to the cloud. But let's say that then, one day the full stack engineer of the cloud comes to us and say, look, you are sending all this data, but basically what I'm doing is taking this 10 data and averaging all 10 together. So then you can say, well, I can do that on the device. I can, sample the 10 data, do the average, and just send one single value over to the cloud, right? So that's something I can do. And so basically,
let's see what is the difference.
Yeah, we're gonna flash basically this new firmware, which you can look at the code, but basically what it's doing is doing the average of the 10 different values and sending a unique value over to the cloud.
Okay, I am very curious.
So we are starting from 130 millicoulombs. Yeah. So let's see if it's done program. Yeah, it's done. Reset it. So let's wait for a new event. Okay, we can see here we just sent only one value. And see?
Mm-hmm.
Here we go,
46.
46. Yeah, it's almost a third. So, you know, simple trick, your battery life is 3 times.
Double, 3 times, yeah.
Yeah, yes, 3 times higher. Yeah. Of course, I mean, you are averaging, so you're losing some information, but maybe, you know, that's a very trivial example, but maybe you can use like some compression algorithms or something like that, you know, to compress the data and just send fewer data over to the cloud. You know, it's something that you can think, you know, once you know where you are spending your energy, you know where you can basically tweak the firmware to optimize. Exactly.
Wow, I would. These are very interesting views, because normally you may never think like sending 10 values instead of one value is going to save half or over half of the battery life, because it looks like there is no difference.
Yeah, I mean, remember, we are talking about low power, ultra low power device. So, you know, I did a presentation.
Every instruction counts.
Yeah, every microcoulombs counts. So, and we are not in the Bluetooth Low Energy. I mean, if we do it, we do it exactly for the Bluetooth Low Energy. We'll see that, you know, current consumption is even lower, and batteries are usually, you know, smaller, like a coin cell. So, you know, every microcoulombs counts in that case. So yeah, I would say I did a presentation, and the title was every little microcoulombs. So, you know, every microcoulombs counts in this kind of application.
Cool. Do you have something else, or open the
no,
presentation? I think did we go through everything?
Yeah, I think we did.
What is in the links?
Yeah, well, just the data sheet and lithium-ion battery.
Okay,
and
go up.
The kits.
Page number 6. What is on page number 6?
Was just, you know, how to do the setup and yeah, the setup basically of the experiment.
Okay. So what do you exactly do? You mentioned you designed this board, or you mentioned you design it because you do development for clients.
Exactly. I mean, we are a small design house based in Italy, and we help our clients in designing embedded systems. And mainly we are focused on battery powered devices, but not only. And and we offer different services like electronic design. So, you know, we can design your PCB, starting, you know, from the architecture, defining the components, designing the schematics, doing the layout, and help you build the prototypes, because we can also build prototypes in a house. We do software developments, so we use all this kind of microcontroller used in the IoT world. We can use rapid prototyping if needed. We build automatic test systems to test the electronics. And we also help our customers with getting the certifications that they need for their products. So we try to do, like, you know, a full services around embedded products.
If someone would like to buy your board for testing, can they do that?
Yeah, they can do that. At the moment, you basically need to send an email on the info@altutech.com, and you can buy the boards. And as I
May I
said,
ask how much is it? I'm just curious.
No, I don't have the numbers
Okay, you
at the
don't
moment.
know.
Yeah, but, you know, it's definitely cheaper than the jewel scope because you need the jewel scope as well. So, but yeah, no, they're cheaper than the jewel scope. And you also have, you know, here, well, you can. I mean, actually, the schematics are open, so here you can see all the schematics.
These are the new Altium 365 I see in the
Exactly.
bottom left. So you can directly
Exactly.
actually view the data from Altium.
Yeah. Yeah, you can navigate through it, select the components, see all the data, see where it is on the PCB, on the 3D. You got also Draftsman. So yeah,
Nice.
and it's also to showcase, how we operate. I mean, if you ask us to develop a board, you're gonna have this kind of outputs, and then you got the BOM as well. And then, as I said, we also provide an Arduino board package to use these boards. So yeah, you can use it to test the board and within an Arduino environment. So very user friendly. I just want to point out that in these examples, basically we are using a scheduler that we have developed. So a custom scheduler, which is on the board package itself. Because I mean, if to go in deep sleep, there is one thing we haven't talked about is the fact that when we go in deep sleep, the microcontroller is basically in reset. So you're basically losing all your data in RAM, everything. So if you're used to, for example, using FreeRTOS, you can't use deep sleep because you're losing all the states of your or real-time operating system. So it's not easy to use deep sleep unless you use like a scheduler that we have done. So you're a way to save data in the RTC memory of the ESP32, which is not losing data when you go in deep sleep. And you
And then
need to
restoring
use
after you wake up.
exactly. That's exactly what you have to do. And so it's a bit trickier to use deep sleep compared to other sleep modes like light sleep, which is used by FreeRTOS, for example. But the current saving is huge. I mean, if we look at the data sheet in light sleep is 130 microamps compared to the 5 microamps in deep sleep. So there is a pain, but there is definitely a reward.
Thank you so much, Andrea. This was super useful, and after after watching this kind of videos or after talking about this kind of topics, then I always would like to buy all the kind of different devices for playing.
Yeah, I mean, it's we are also open to suggesting some device which they think is going to be useful to characterize. We can make the board and make it available on our website, because once you buy the gyroscope adapter, we're going to basically make all the board with the same interface, so you can reuse it to connect to different boards that we provide. And this adapter is also, I mean, we are also planning to do the adapter for the new gyroscope, which is the newest one. We haven't done it yet, but it's definitely on the roadmap.
And this old one is cheaper, or they don't sell it anymore? If you go to gyroscope,
I think it was the same price. Let me check if I can find the price of the old one. Sold out. Yeah.
So they don't sell it anymore.
Yeah, they don't sell it anymore. Yeah, it's definitely time to move to the newer one.
What is different? I'm just curious.
Right. So basically, the main difference is that here you have an independent voltage and current meter. Whereas in the gyroscope 110, the one I'm using, basically you're measuring the current, but you're measuring only the, I believe it was the output voltage. Here instead you have a two independent voltage and current meter, so you can measure whatever voltage you want. So it's just you have a two connection to wherever you want. You can measure something else, not only the output voltage. So that's the main. Well, there are other differences for sure. Probably it's more precise. Yeah, it's a higher resolution. Maybe
0.5 nanoamp resolution.
Yeah.
Wow.
Current range is higher, and yeah, and I think is also more rapid in terms of switching between shunt resistors. So yeah, there are, I mean, sensible differences. So
nice.
Yeah, I'm definitely gonna buy it. I mean, it hasn't been released too much time ago. Maybe 6 months ago. I'm not sure about that. I may be wrong, but definitely I'm gonna buy one and use it with our for our power consumption measurement activities.
If I had one, I would use it, because
Yeah.
sometimes I design these small boards like ESP and other stuff, and I really would like to know power consumption for some of the applications what I have in mind. So
Yeah.
it would be super useful. Okay,
Yeah.
thank you, Andrea,
There
again.
is, maybe just one last thing. You
Okay.
there is one
Oh,
other application that I use, the Juice Scope. So I have this front panel with USB, and it's very useful. I can give an example. We just designed like a product which is basically a USB key, like a MOS storage with some special things. But basically, we want to make sure that we are compliant with the USB and rush current standard. So basically, when you have to certify the device, they will plug into USB and measure how much current you draw in the first 100 milliseconds, and you have to be below certain levels. So with the Juice Scope, if you have this front panel, there is an automatic plugin that you can use it, and basically you can immediately know if you are in or out of the spec.
so
So
it will show the limits or something?
yeah, we'll measure the current, and then you can connect to this plugin, which basically will get all the data points from the Juice Scope, and will tell you if you are within the specifications. So you can use to basically do the pre-compliance of the USB and rush current if you have a USB powered device.
Nice,
So it's very useful.
nice. Anything else before I say thank you very much again?
Oh, I'm fine. I mean, if in the future we want to do the same with the NRF52, we have the board. I have it actually right here. So, we can do maybe in the just video for the future where we can say, I mean, for example, with Bluetooth Low Energy, again, you can tweak the software. For example, you can tweak the TX power of the transmitter, so we can see actually a difference in power consumption. You can tweak how often you advertise, so how often you say to the world that you are here, and that will save the power as well. So we can maybe in the future do a video
Okay,
and
I'm
see
just
how
curious, do you
things are
know
changing.
how much lower it is, like comparing to the 5 milliamps what we measured today?
The average, I mean, for a Bluetooth Low Energy application, we are talking, I mean, general application, we're talking between 50 to 100 microamps average current.
Really?
Yeah. You can be even lower if you don't advertise too often, but then it's trickier to connect to a cell phone. I would say that the ballpark is between 50 to 100 microamps.
That's much lower than Wi-Fi.
Yeah, absolutely.
100
I mean,
times
it's
lower.
as a lower range, and you need to go on with the phone and connect with the phone. It's not like Wi-Fi, which you have a connection ready to internet. It's a bit different, but yeah, it's definitely lower.
Okay, let's see how this video will be doing, and if someone is interested also see the numbers for Bluetooth, they can leave comments,
Yeah,
and then we can do also another video.
absolutely.
Okay, so thank you very much, Andrea, again. It was super useful, and I learned a lot. Finally, I know how much current my ESP32 is driving.
Yeah, nice to talk with you, Robert. It was really nice. Thank you.
And that's everything. Thank you very much for watching this video. By the way, we are preparing some very interesting tutorials, so if you don't want to miss them, hit the subscribe button. If you want, you can also check out our Fedevel online courses, where you will find everything important from basic board design up to advanced hardware design and PCB layout. The link is in the description. That's all for this video. Thank you again. Don't forget to leave your comments and see you next time. Bye.